Good day, everyone. This is the first follow-up video of the first video lecture on analysis and calculus, which is about maximum, minimum, supremum, and infimum, and all those stuff, right? And in this video, this follow-up video, we're going to cover exponential function, which is related to supremum. But how? How are exponential functions related to supremum? Like, they seem to have no relationship at all. Why? Like, how are they linked? How are they connected? How are these two supposed to be, related to each other? Now let's think of exponential functions. Exponential functions is where the independent variable is in the power. It's the power of some positive number, right? So say we have a positive number a here. As written here, we have an a positive number raised to the q's power, where q is now the independent variable, and our outcome is the a to the q. Now, when we were defining exponential functions for integer powers, like specifically positive integer powers, we know what? We know when a is raised to the qth power and q is a positive integer, we mean to multiply 1 by a for how many times? By a for how many times? For q times, right? So we can have this product notation, like to multiply by a for q times. Multiply who by a for q times? To multiply 1 by a for q times. Right? And then, what if q is equal to 0? We're trying to extend this, right? What if q is equal to 0? When q is equal to 0, we mean to multiply 1 by a for 0 times. To multiply by a for 0 times means not to multiply by a, right? Right, so if not to multiply by a, then what are we left with from previously? Right, we auto multiply a by q times. Now we don't multiply that by a, that means we're left with 1. So when q is equal to 0, that's 1. But we're left with 1. And then they continued on. If positive exponents corresponds to multiplying something by into 1, right? Multiplying 1 by something, then negative indices would mean what? Negative exponents would mean what? Dividing 1, right? Positive and negative are like reverse of each other, inverses of each other. Then of course, if positive is multiplication, then the inverse of positive should correspond to the inverse of what? Of multiplication. Inverse of positive is negative. It means negative corresponds to the inverse of multiplication. Inverse of multiplication is what? The reversed operation of multiplication is division. So negative integers gives division. And there we we've dealt with every single integers. Are we satisfied? No, mathematician says no, we are not satisfied. It's not enough. We need rationals. And so they came up with rationals when q is equal to 1 over n, where n is non-negative and non-zero integer. Non-zero integer. N is a non-zero integer. And they defined this time a to the 1 over n as the positive root of x to the n equals a. Why positive? Because we are assured that there must be a positive root for integer n that is non-zero. If you look at the graph, you'll find out that it's just approximately looks like this. Looks something like this. I'm too lazy, I'm just gonna move it over. Yeah? It's approximately something like this. My drawing skills are not good enough. Right, it looks approximately like this. I don't care what's happening on the second and third quadrant, but the first quadrant must be like this. That means when a is positive, we are assured to have a positive root, right? We are sure to have a positive root. And we take that root as a to the 1 over n power. Alright, we define that root as a to the 1 over n power. Then we can generalize the law of indices all the way up to rationals to end up with this definition for Q equals M over N. Right? We just need to replace this A with A to the M. And there we have it. We have all rational numbers. Are we satisfied? No, mathematicians say again, no, we're not satisfied because we still have irrational numbers to deal with. Irrational powers? Let's say we have a positive number 2. Let's say we have 2 raised to the square root of 3. What does it mean by raising to square root of 3? It doesn't really mean that. It doesn't make sense. Right? It doesn't even make sense. If I say, oh, 2 is raised to the square root of 3 means what? Means we have to multiply 1 by 2 for square root of 3 times. Are you kidding me? Is that gonna make sense? No, right? You can't possibly say that pie is really a pie. That for eating, you know. You multiply the radius by 2 and then by a piece of pie to get the circumference. No, you don't do that, right? You don't do that. So what do we mean by raising to an irrational power? What do we mean by raising to an irrational power? We have to think of properties of real numbers. Now, for any two irrational numbers that are unequal, any distinct two irrational numbers, there must be a rational number in between, right? So if we pick an irrational number larger than say it's positive, then from 0 to that irrational number, let's call that x for the moment. Let's call that x. It's irrational. From 0 to x, there's going to be an infinite amount of rational numbers. So there's going to be infinite amount of rational numbers. And a raised to the rational power, this sequence is strictly increasing. It's strictly increasing. So if you choose any two distinct rational numbers, if one is smaller than the other, say a is the smaller one and b is the larger one, both rational numbers, a is smaller than b, then some other positive number k raised to the a's power is definitely going to be smaller than k raised to the b's power. How is that going to help us? Now we have a strictly increasing sequence, right? Because from 0 to x, that irrational number x, there are infinitely many rational numbers, right? But still we have an upper bound. We can choose the rational number that is just a little bit bigger than x. Let's say it's q. I'll draw it on a number line. Let's say this is 0 here. Excuse me. Say this is 0. I have to draw a number line. I'm going to deal with the positive side here. I'm not going to demonstrate the negative side, but you can just extend things over there. So, let's say x is over here. So there should be a bunch of rational numbers within this range, right? From 0 to x. And then I can choose, say, this is q, right? As before we said, this is q. This is q. Just the rational number just a little bit larger than x. Then q is an upper bound of a to the r, right? Where r belongs to rational numbers intersecting the range from 0 to x. Right? There's gonna be an upper bound. A to the q is going to be the upper bound of the set. A to the q is an upper bound. We have an upper bound means what? Means supremum of the set. supremum of this set exists. Right? Supremum of this set exists. Then what? Then we can say, since R is within this set, we can define now a to the x is just the supremum of this. Right? Right? Because again, if we have an x, we have a q, then we can still continue on, find another q here, q1, let's say this q1, smaller than q, and still these two are rational numbers. Right? We can find another rational number that is even closer to x than q. Right? Then we can just define a to the x, this irrational number, as what? As the supremum of the set. Of the supremum of the set as we get a closer and closer to x, right? We can define that as a supremum. So that's how we define irrational powers. Now, once we have this definition, then we should start to think. We got laws of indices before, right? And your teachers would probably tell you that it's gonna be true for any real numbers, just use that as a given fact. But is it really true? Now we have this definition, can we prove or verify that it indeed is true? Yes, and I'm going to do only one case. I'm going to prove one law of indices, one case of one of the laws of indices for you, and the rest would be, as in textbooks, left for the readers as an exercise thing, because the video is going to get infinitely long. So I'm going to just do one case. The case would be a larger than 1, a to the alpha times a to the beta equals a to the alpha plus beta, where alpha and beta are any real number. Any real number. I repeat, any real number. Now, if we've proven this, then by a tricky little substitution, you can prove the case for 0 for when a is in between 0 and 1. Now, why am I not doing a equals 1 case? Why isn't there not a third case for this law? Because it's apparent, because 1 raised to anything is just 1, so the supremum is going to be 1. 1 times 1, of course, is going to be 1, right? This is going to be 1 as well. 1 times 1 is 1, verified, apparent, that's obvious, so I'm not going to do that. You don't really need to do that, you just need to do larger than 1 and within 0 and 1. So I'm going to do the larger than 1 case, and the rest is going to be left to you as an exercise. If you can spot that tiny, tricky little substitution, it's cleared, alright? So. It's supremum, right? So let's deal with the supremum first. Since we have supremum here, that means for all epsilon larger than 0, by definition of supremum, we know there's gonna be a rational number r, smaller than or equal to x. Now let's not use r because r is used above. Let's say it's q. Q smaller than or equal to x such that when a to the x, it's the supremum, right? The supremum minus a little bit would not be supremum anymore, would not be an upper bound anymore. Not be an upper bound means it's smaller than some kind of element inside the set. Right? Supremum minus just however tiny it is, you subtract that from the supremum, it's not going to be an upper bound. Right? So that's the definition of supremum, and we can continue on with that. Let's see. A to the alpha, a to the beta. So we can rewrite this. We can rewrite a to the alpha and a to the beta using some definitions. For all epsilon larger than 0, there's gonna be the definitions are using x and x's, and we have using q and r as well. What else? What other letters can we use? I don't really want to use I and j because that kind of coincides with the the imaginary units and the quaternions and all those stuff. Let's use m and n. It's gonna be m smaller than or equal to alpha, rational number, as well as n smaller than or equal to beta rational number as well, such that a to the alpha minus a little bit, it's defined as the supremum, right? Supremum minus a little bit is going to be smaller than a to the m, something in the set. A to the beta, again, the supremum, minus epsilon smaller than something in the set, a to the n. Now, m and n are what? Are rational numbers. That means a to the m plus n can be safely written as a to the m times a to the n, which is going to be larger than what? We just multiply these two together. Now that's going to be larger than a to the alpha minus epsilon, a to the beta minus epsilon. And something else to notice, exponential functions are strictly increasing. If you want to prove that, you can go on. It's easier than proving this, so yeah, I'll leave that to you. Yes, left to the readers as an exercise. Again, yes, I know, because I don't want the video to get extremely long. Probably if you want me to do the proof, I can do it in the next video, but still, let's just assume this as a fact first, as a given fact first. It's strictly increasing. M is smaller than alpha, n is smaller than or equal to beta, so m plus n is going to be smaller than or equal to alpha plus beta. This is smaller than alpha plus beta, so this a raised to m plus n is also going to be smaller than or equal to a to the alpha plus beta. Now, from this, I can extract these two parts out, and I can say for all epsilon 1 larger than 0, not epsilon now because we have to separate epsilon and epsilon 1. For all epsilon 1 larger than 0, I can say this is a to the alpha times a to the beta minus epsilon 1. It's going to be smaller than or equal to a to the alpha plus beta. Excuse me, not smaller than or equal to, because this is smaller than. Not that's a strict inequality. Right? Why? Now look, this is a to the alpha minus a little bit. This is a to the beta minus a little bit. So of course this is going to be smaller than a to the alpha times a to the beta, right? It's going to be smaller than a to the alpha times a to the beta, apparently. If it's smaller than a to the alpha times a to the beta, I can say it's going to be equal to a to the alpha times a to the beta minus something. And that something is completely determined by this epsilon. Right? If I want this thing to be large, then what? Then I make epsilon larger. If I want epsilon 1 to be small, then I make epsilon smaller. Right? So epsilon 1 is still an arbitrary constant, completely dependent on epsilon. But still, it's arbitrary because epsilon is arbitrary. So we have this. If a number minus some arbitrary thing would immediately be smaller than something else, then we can conclude that these two numbers has such a relationship. A to the alpha plus times a to the beta, our first number, subtracted something would be smaller than the other thing, then it's either have to be originally already smaller, right? If it's originally smaller than that thing already, then no matter what you subtract, as long as you're subtracting a positive number, still going to be smaller, right? Can be smaller than a to the alpha plus beta. But can it be equal? Can they be equal? Yes, because when they are equal, if you subtract something from one side, it's going to be smaller, right? That side's going to be smaller. So they can be equal as well. Now we've only proven half of it because our aim is to prove that the two sides are actually equal, not smaller than or equal to. We've not finished our proof yet. We have not finished our proof yet. But we can do something, a tricky little thing. Because what? Because we started with left-hand side here, so we can also start with right-hand side. For all epsilon larger than 0, we can still say that we have a rational number p How did I write that? All right, we have P rational, and P is smaller than or equal to alpha plus beta, not A, alpha plus beta, such that A to the alpha plus beta minus epsilon is gonna be what? It's gonna be smaller than A to the P. Now I can also make this P smaller than or equal to R plus S, right? I can also make this P smaller than or equal to R plus S. Because R and S are what? Excuse me, not R and S. Kind of confuse it. M plus N. I can make this P smaller than or equal to M plus N, right? They have this sign, these two relationship anyways. So we can make this P, we can force this P to be smaller than or equal to M plus N, so that this, by the strictly increasing property of this exponential function, we can end up with this. Right? And M plus N are what? From before, we know they are rational numbers. So this can be written as A to the M times A to the N, and then the same thing goes on. A to the M times A to the N, smaller than or equal to A to the alpha times A to the beta. Right? This would mean this thing is strictly smaller than this. Right? So A to the alpha plus beta minus epsilon strictly smaller than A to the alpha times A to the beta. Same thing. It's gonna end up, and we're gonna end up with what? We're gonna end up with A to the alpha plus beta. It's gonna be originally smaller, right? Minus something gets smaller than the other. Minus, no matter what, it's gonna be smaller. So it's either gonna be originally smaller, or it's gonna be equal. Hey, look, we got what? We got this and we got this. Meaning what? Meaning what? Look, the left hand side and right hand side are like reversible without needing to change the sign. That means what? From these two we get, from both of them we can get A to the alpha plus beta is equal to A to the alpha times A to the beta. Right? If it's small, if one of them are smaller, then we should have the other sign reversed. They should not have the same sign in between, right? But they do. They do have the same sign, so the only possible case is that they are equal. And there we've proven one of the laws, one case of the laws. And if you can spot one of the that tricky little substitution, you can prove the other cases, and the rest of the laws are similar. Actually similar, very similar. And there we end our lecture here. So let's get back to what we have all went through. First thing, we started with exponential functions. We went through how it was defined on integers and rational numbers. And then we came to think how we can define exponential functions using supremum, right? How we can define exponential functions where the exponent is irrational. Right? When it's irrational, we don't know what to do. So we kind of think of supremum using sets. We try generalizing things from rational to irrationals using the property of real numbers. And then we end up with exponential functions having this definition, this definition written in black, right? And then found out, surprisingly, that this definition is not going to violate our laws of indices, so that means we can safely generalize our laws of indices all the way up to real numbers. And yes, we've went through one case of the proof of one of the laws of indices. And if you would like to prove the rest of them, you can proceed. It's gonna be very similar to this proof. So I'm not gonna do that here, and it's gonna be like left for the readers as an exercise as I go through that sentence over and over again. You know, left for the readers as an exercise like all textbook does. So it's not gonna be hard. If you're interested, you can prove it. If you're not, then just keep that as a fact. And that is the end of this video lecture, and I hope you enjoyed it. See you next time.